Hello friends, the Super Bowl streamed live on Paramount Plus, one of the fastest growing streaming platforms where millions of us watch their favorite movies, series and most anticipated live events like the Super Bowl. To manage the large volumes of data and traffic, the Paramount Tech team had to learn the art of scaling across multiple cloud regions. Early in 2023, the Paramount Tech finalized their migration to a multi-region architecture, and since then, the streaming platform has been operating across multiple regions in Google Cloud and running on a new distributed SQL database. And as the 2024 Super Bowl approached, Paramount Plus made several announcements, highlighting that the new architecture was paying off. For instance, NFL on CBS scored the most watched NFL divisional playoff game ever with more than 50 million viewers. Later, NFL on CBS delivers the most watched AFC Championship game with more than 55 million viewers, and Paramount Plus recorded its most streamed live event ever. So how has Paramount Plus achieved this level of scalability across multiple regions? Let's do a deep dive. Scaling the application tier across multiple regions is usually a no-brainer. All you need to do is to pick cloud regions for your application, then deploy application instances in those regions, and finally configure a global cloud load balancer that will be routing and load balancing the user requests across all of those instances. However, things get more complicated when you need to decide about a multi-region database deployment, especially if you're dealing with transactional workloads that require low latency and data consistency. One of the obvious solutions for the global data consistency is to deploy a single primary database instance in one of your cloud regions. But with this approach, you will be dealing with two trade-offs. The first one is the latency. The latency will be low only for those users who live close to the region with your database deployment. Other users will face much higher latencies because their requests would need to travel across the country to get to the database that is deployed in other region. And the second trade-off is high availability and fault tolerance. As long as you're running a single primary database instance that handles both read and write requests, if the region of the database deployment goes down, then your entire application becomes unavailable. And the Paramount Tech Plus team acknowledged that the database tier posed the biggest architectural challenge during their migration to a multi-region architecture. They narrowed down the criteria and after some internal research, selected YugabyteDB, a new distributed SQL database that can function across multiple regions and other distant locations. Let's learn a little bit more about YugabyteDB now. YugabyteDB is a distributed SQL database that is built on PostgreSQL. You can literally think of it as a distributed version of Postgres. Usually you run YugabyteDB in a multi-node configuration with nodes spanning several servers, availability zones, data centers, and cloud regions. The database shards all your data across the entire cluster and then uses the wrapped consensus protocol to synchronize the changes across the entire fleet. When it comes to a multi-region configuration, there is no silver bullet solution. YugabyteDB suggests to pick from 8 design patterns for multi-region applications, and your decision will be based on the trade-off between the latency, performance, and high availability. Today, I want to take a look and play with two design patterns. The first one is the global database with a preferred region, and the second one is the follower reads. So let's play with them and see how they work in action. A sandbox for my little experiments looks as follows. I provisioned 3 commodity VMs in 3 regions of the United States West, East, and Central. All of those VMs run a node of my YugabyteDB cluster. So effectively, I've got a multi-region YugabyteDB cluster spanning the entire country. If I go to the nodes of the YugabyteDB UI, I will see that yes, every node runs in one of the cloud regions, United States West, East, and Central. And the first multi-region design pattern I want to experiment with is the global database. The pattern assumes that you spread your database across multiple zones or regions. On failure, a follower in another region will be promoted to leader in seconds without any data loss, and applications read from source of truth, possibly with higher latency. You can minimize the latency by configuring a preferred region, and by doing that, all the leaders for all the data will be located in one place, and this way you will minimize the amount of cross-region traffic. So this is how I use this pattern in practice. As you remember, I deployed a single YugabyteDB instance across 3 regions. As a result, if any of these regions goes down, I remain operational, I'm not losing any data, and I will keep serving the user requests. From the latency standpoint, I selected the United States East as a preferred region. All the primary copy of data, all the leaders will be located in that place. And as a result, the latency for those who live in the United States East will be the lowest. The latency for the other users from other locations will be higher. But no worries, my friend. Going forward, we are going to take a look at the second design pattern for multi-region applications that will make the read latency comparable across all of the locations. But as of now, let's test what I have already created. I'm connected to my virtual machines in those 3 regions. That's my virtual machine in the United States East, West, and Central. What I'm going to do next? I want to start a sample application. I'll talk about it a little bit later. So now the application will start and it will connect to the database node in the East. That's the preferred region. I want the instances to get connected to that location straight away. And we are repeating the same operation for the West and then for the Central location. That's a Spring Boot application that's successfully connected to my YugabyteDB cluster. What the application does? This is a movie recommendation service. You can ask questions in plain English and it will perform a vector similarity search over the movie database that is stored in YugabyteDB. And all I need to do is to send this request to the following API endpoint, and I'm asking, I want to watch a movie about a space adventure with unexpected ending, and the rank of the movie needs to be 7 or above. Let's send this request and take a look at the latency. Now I'm sending this request from the United States East location that is close to the preferred region. And the latency for this request is around 9 milliseconds. Wonderful, right? So let's see what happens if I send the same request but from an instance that is located in the United States Central. We are repeating this several times. And you will see that the latency is higher. It's around 134 milliseconds. Why so that? Because this request needs to travel first to the preferred region in the United States East, and then the database will perform vector similarity search, and then my application in the United States Central needs to receive this long result set with information about suggested movies, Interstellar, Gravity, and Star Trek. How the latency looks like for those who live in the United States West. Running the same API call, repeating this several times. And the latency is even higher, it's 246 milliseconds. And the story is the same. The request needs to travel through the country to the United States East, execute there, and then process this lengthy result set. And this latency will be reasonable for many multi-region applications, but I'm not satisfied yet. What I want to do is to have the same read latency across all of the locations, whether you live in the United States East, West, or Central. And 9 milliseconds is going to be my baseline. For that, let's take a look at the second design pattern, the follower reads. The follower reads pattern lets my application instances in the United States Central and West locations read data from local database nodes from local followers instead of going to the database leaders in the preferred region of the United States East. And with this configuration, the read latency will be comparable across all of the locations, although the followers might not hold the most current data at the time of a request. For instance, there might be a 30 milliseconds data lag on the database node in the United States Central, and a 65 millisecond data lag on the United States West node. Why so that? My multi-region cluster is configured with the replication factor of 3. This means that a transaction would be considered committed once 2 nodes out of 3 confirm the changes. So if the United States East and Central nodes acknowledge the transaction, the United States West node might still be recording this change, and this explains the lag during follower reads. Despite this potential data lag, the entire data set on the followers is always in a consistent state across all the tables and other database objects. And this is more than enough for my application, for my movie recommendation service, because I'm not updating my movies catalog every 100 milliseconds, right? Now, why don't we try this pattern in practice and see how it improves the latency across all of the locations? I'm back to my terminal window, and now I want to restart the application instances in the United States West and Central, reconnecting them to local database nodes and enabling the follower reads. To do that, I have another script. I'm using this for the West. The West connects to the database node from the West. And also I need to say enable follower reads. And repeating the same for the central location. The central instance connects to the database node from the same place, and also we are enabling the follower reads. Excellent, everything is good to go. Now let's execute the same HTTP request that returns movies about space adventures with unexpected endings, and we are going to send this request to the United States Central location. Let's run it a few times, letting the application to warm up and open the database connection. 1, 2, 3, and you can see that the latency right now is 13 milliseconds, which is very close to 9 milliseconds that we have in the United States East. How about the latency in the West? Running the same request, letting the application to open and warm up our database connections. It takes time in the beginning. But then once you keep executing this request, you'll see that the latency is around 10 milliseconds. And this is how you can take advantage of the follower reads in your multi-region application. As a result, users of my movie recommendation service will have the same experience regardless of their whereabouts. Why? Because the read latency is the same across the country. However, before we finish, let's quickly talk about the write latency, because we are dealing with a transactional database, which means that when you execute a distributed transaction, the change needs to be replicated across 3 regions. Let's do a simple experiment. Jumping back to our application instance in the United States East, assume that I like the suggested movies. I want to watch the Star Trek, I want to watch the Gravity, and also I am a fan of Interstellar. I want to add those movies to my watch list, to my library, and I'm going to do this from the United States East instance that is connected to the preferred region. Let's take a look at the latency. First, I want to clean my movies catalog, and let me execute this request. You'll see that it takes 71 milliseconds on average to add those movies to my catalog. Why so that? Because the request comes to my preferred region, and that the preferred region needs to replicate this change across the United States West and East. Now let's see how the latency would look like if I decide to update my movies catalog from the United States Central and West. Okay, updating the movies catalog from the central location. And the latency is around 100 milliseconds, 30 milliseconds higher than from the East, which is expected. And let's do the same for the West. Yeah, the latency is around 130 milliseconds. Why is the latency higher in the West and Central location? The laws of physics, the application instance from the West and Central first needs to send this update to the preferred region in the United States East, and only then, from that East location, this distributed transaction will be executed and replicated across the entire cluster, across the entire country. That's why the higher latency. However, does it mean that the write latency in multi-region deployments will always be high? Not at all, my friend. If you go back to the design patterns for multi-region applications, you will find that there are several patterns that will help you to design a solution for low latency reads and writes across distant locations. One of those patterns is geo-partition deployment. With that pattern, the user data will be stored in the location close to the user, and this is how you will be able to achieve single-digit millisecond latency for both reads and writes. But this deployment pattern goes beyond the scope of this video. That's why for today, the job is done. How do you like this, my friend? Isn't it cool? Today you could witness that multi-region applications are not inherently slow. You just need to pick and implement the right pattern that is right for your application. The Paramount Tech team mastered the art of scaling by building a streaming platform that can accommodate millions of users during peak periods, including the live events such as the Super Bowl. So now you go ahead and study the multi-region deployment patterns and start building applications that scale and never fail. Bye bye now.